Welcome to Chapter 14, Part 3. In this video, we're going to talk about mass spectrometry. It's a little bit different than spectroscopy. We're not focusing on light's interaction with matter in the same way, but it is an important technique for characterization because it allows you to determine molar mass. Right? So mass spec helps us to determine molar mass. And we'll talk about how it's possible, it can help you actually determine formula of a compound. So it's really necessary if you have an unknown, and it's helpful additional information if you've made something new. We're going to look at how the experiment works, and we're going to talk a little bit about how to read a mass spectrum. In this video, we're not going to go as in-depth as possible, but there are some takeaways I want you to know about this type of experiment. Now, the experiment itself has some key parts. Your compound needs to be vaporized, ionized, and it will undergo fragmentation. Those fragments will then be detected, and the results will be graphed. Now, this is a very simple diagram of the mass spec experiment, and there's variations. There are different types of mass spec instruments out there, but this gives you a basic idea. So for this to work, your sample needs to be in the gas phase. So there will be some sort of heating element at the inlet that will vaporize your sample. And then ionization. Electron impact is the most common, and that is what we're going to talk about here. We take a beam of high energy electrons and just bombard your sample. This causes ionization. Right? When those electrons hit your sample, it allows for another electron to pop off, and you wind up with a +1 ion. Sometimes that also leads to fragmentation, which we'll talk about later. There is some sort of acceleration area to speed those particles up, and then they enter a magnetic field. Since they're charged, the magnet is going to cause their path to bend. The heavier they are, the less they bend. The lighter the fragment is, the more it bends. That mass to charge ratio of those particles is detected, and then these results are sent off to some sort of chromatogram or computer where you would get an actual spectrum. All right, so in that first step, ionization, right, we're not looking at a specific compound here, just something organic, has carbon-carbon bonds in it. When you hit with a beam of high energy electrons, right, it's going to give enough energy to this compound that one of those electrons is going to pop off. That's why this works. You need this charge. Now, an electron has negligible mass in comparison to protons and neutrons. So if this makes it all the way to the detector, you're going to get mass to charge. Z stands for charge. And that charge is always +1. So mass to charge is also the same thing as figuring out the mass. All right, those radical cations, however, are not super stable. All right, okay, I guess we'll keep track of some vocab here too. All right, the molecular ion, or the M+ ion, that's your parent. All right, that's what tells you the mass of your compound is going to be a parent peak. It has a plus charge because that is needed to make it through the mass spec experiment. But unfortunately, or I guess fortunately, because you can use this information to determine other things about your compound, that radical cation is often not very stable. and will fall apart. And so if it does fall apart, you may get fragments. Now, the radical fragment doesn't get detected. It doesn't have a charge, so it doesn't get deflected, and you never see it. But the positively charged cation fragments will make it to the detector, and you will see a signal for some peak that is smaller than your parent. Right? So when you get a mass spectrum, there's typically more than one peak present. Now, in this case, we're looking at methane, so the parent right there is at 16, but you do see some at 15, so where we had some fragmentation and loss of a hydrogen. A little bitty fragment there at 14, where we lost 2 hydrogens, 13 and 12. We will come back to the little tiny peak at 17 in a minute. Another piece of vocabulary here that's important, the base peak is the tallest. Sometimes the base is the parent and sometimes it is not. The fact is the tallest peak just means that's what you had the most of, right? It's the tallest, it's the most abundant. When you have something that is relatively stable once you ionize it, it doesn't tend to fragment as much. So, for instance, and there's just the different fragments we saw for methane. Okay, before I move on to fragmentation, mass spec, just like IR, has applications in many different fields. Because you can use it to find molar mass of unknown or identified compounds, it has a lot of usefulness in pharmaceuticals and biotech, even forensics, and environmental testing. There's a lot of applications for this particular technique. What I want us to compare here is we're going to look at benzene versus an alkane, and a straight chain open alkane. When you ionize benzene, for the most part, it stays together, right? You have your peak here that is both your parent and your base peak. It is the tallest. It represents benzene, which has a mass of 78. Again, we'll talk about that little N+1 peak in a moment. And you do have fragmentation, but you don't have a lot of fragments concentration-wise, right? The most abundant is that M+ peak. However, when you take something like pentane here and you bombard it, it fragments much more easily. So we have our parent here at what looks to be 72, but it is not the base peak, right? The most abundant peak is down here around 43. So the mass of pentane is not 43, but that is going to be the most abundant fragment that was there, right? So the parent is what tells you the molar mass right here. You can get some information from the mass spec beyond just the molar mass. And there are 4 different things I want you to keep track of. One is the nitrogen rule. If you have an odd molar mass, right, so an odd parent, that typically indicates you have an odd number of nitrogen in your compound, right? So if it's even, that doesn't tell you that you don't have nitrogen. It just might be it's an even number of nitrogen. But if you have an odd molar mass, you most likely have nitrogen. Just the way that it bonds often gives you an odd number. The M+1 peak is also something you need to watch out for. So I mentioned this earlier, this little peak here, and now this is where we learn about it. This has to do with the C13 isotope. So the molar mass that you see on the periodic table is a weighted average, and it takes into account naturally occurring isotopes. When fragments hit the detector in a mass spectrometer, it's not going to take averages. It's going to take the actual mass to charge ratio. So if you have carbon 12, then it is going to have a molar mass of 16. But if it has carbon 13 in it, it will have a molar mass of 17. Carbon 13 is a little bit less than 1% abundant, right? About 1% of all carbon atoms. So this peak here should be 1% of that parent because there's only one carbon present. Sometimes you can't even see that N+1 peak because it'll be so tiny, but that is where it comes from. If you have more carbon in your compound, so in methane, you're going to see the N+ peak at about 1%. However, as you add more carbon, the likelihood that you're going to get a C13 increases. And so you can see with decane that the peak is much bigger on that N+1. It's not likely that you're going to have two C13s in one compound, or in one molecule, but the likelihood that you would have one increases. And so this peak gets larger. There is some fun math that you can do to take the height of your N+1 peak to help you determine how many carbons must be in your compound. I am not going to ask you to do that, but that is one way that you could use mass spec to analyze your unknown or your compound. The other two, so we have nitrogen rule, we have the N+1 peak due to carbon 13. There's two more rules I would like you to know about mass spec, and that has to do with chlorine and bromine. So we're going to start with chlorine. There is chlorine 35 and there is chlorine 37. All right. There we go, chlorine. The molar mass of chlorine on the periodic table, right, is 35.45 something. It's because it's 76% light chlorine, 24% heavy. Again, you're not going to get a weighted average on a mass spectrum. Some of your molecules are going to have heavy chlorine and some of them are going to have light chlorine. And that is going to be represented in a pretty kind of characteristic pattern. You are going to get an M peak, right? And then an M+2 peak for the heavy. Now, since it's about 3 to 1 light to heavy, you're going to see a pattern of 3 to 1 in your M+ and M+2 peak. All right, and you can see this is about a third the height of your parent peak there. All right, and so this would indicate all of the molecules that had chlorine 35. This is all of the molecules that had chlorine 37. And something interesting here, I can tell that the fragment doesn't have chlorine in it because it doesn't have a M+2 peak that's a third the height. So I'm guessing that this fragment would just be the benzene. Bromine may be even easier because you have bromine 79 and bromine 81, and they're almost equal. It's 51% the light isotope, 49% the heavy. And so you're going to get an M+ and then an M+2 peak that are about 1 to 1. Right? They look very identifiable. Right? You have two big parent peaks or equal size. Then, of course, you see these little guys down here. That's from C13. Again, I would imagine that this fragment is just the bromine breaking off because I don't see bromine in the fragment. So again, I would expect you to know the nitrogen rule to understand where the M+1 peak comes from and be able to identify if a compound has chlorine or bromine based on the M and M+2 peaks. There may be a few questions in your homework about fragmentation, but I am not going to test you over any more fragmentation. The way things break apart can give you information about their structure. For instance, like pentane, you can lose, you start to see recognizable fragments, a loss of 15, loss of 29, loss of 43, right? These are going to be methyl ethyl propyl groups. And you see those in that fragmentation. If you have branching, fragmentation can change, right? You can get different sized fragments depending on where that branching occurs. There's a lot of interesting stuff here with alcohols and amines, but you are not going to be responsible for that. The same with the McLafferty rearrangement. You're not responsible for that. One of the last things I want to talk about with mass spec is high resolution mass spec. The main takeaway here is high res mass spec, a little bit more sophisticated. It's going to give more decimals in your mass, right? And this can make a big difference because we know the mass out several places past the decimal of neutrons and protons. And so the different isotopes we know. And let's see. That is the wrong picture. Here we go. If we just take, let's say, cyclopentanone and cyclohexane, and we run kind of a regular rudimentary or low-res mass spec, they're both going to come out at 84. So you would not be able to use the mass spec to tell the difference between the two. However, high-res mass spec will take this out several places past the decimal, and because oxygen has a different molar mass than carbon and hydrogen, especially when you look further out, you can actually tell the difference between the pentanone and the cyclohexane. Right? They do have different molar masses, but you need that additional resolution to be able to tell the difference. Now, you can't tell the difference between isomers, but you can tell the difference between compounds that have different elements and are just really close. Mass spec is often used in tandem with gas chromatography. It's one way to analyze a mixture. So how that works is you inject a mixture into a gas chromatography column, right? Because of the solid phase inside the capillary column, much like how TLC works, some compounds move faster, some move slower, but they separate. And then as those compounds come out, they go into your mass spec. They get ionized, they get sorted, and there's that magnetic field in there, and then they get detected. So you wind up with a chromatogram from the GC. So in this mixture, there were 5 different things in the mixture. And what you would be able to do is say, I want to know what was in this peak, and then below it, a mass spectrum would pop up. So it allows you to analyze components of a mixture right away. If you are doing mass spec on larger compounds, sometimes electron impact can be too, what's the word they're using? Let's see. Can be too aggressive. It can blow everything into fragments. And if you need to know the molar mass and you can't get a parent peak because everything keeps fragmenting, you might try something softer, something like electrospray ionization. That would be something you would study more if you took an analytical course or a mass spec specific course. In our last video for chapter 14, we will discuss degrees of unsaturation.